Hello, let us begin by writing the Fibonacci function that maps natural numbers to natural numbers. So we take the input n, and as before, we use match to split our computation into exhaustive cases. So n is either 0 or 1, in which case we output 1, or it's the successor of a number n, in which case the Fibonacci number at this point is the Fibonacci number at the previous number plus the Fibonacci number at n. Notice that I'm using the same name n to bind the variable in this pattern. This is not a problem uh, as in normal quantification in mathematics. So if you say for all x, it is still a valid um statement in mathematics, and the inner x will shadow the outer x. So that is what is happening here. So this particular n that I bind in this pattern is this n minus 2. So when I say nat.suck n here, it means the predecessor of the input n, and this n is the predecessor of the predecessor. We can test our Fibonacci function like so. And if I bring up the evaluation window, you can see that the fifth one is 8 because it's 1, 1, 2, 3, 5, 8. So when writing programs, it's more natural to express the Fibonacci function as parameterized by natural numbers and returns a natural number. So with this transformation, you can eliminate the explicit fun binder, and you should read this definition as follows. So fib is a natural number parameterized by a natural number n, and after colon equal to, you state the definition of fib n in terms of n. So we will use such parameterizations naturally whenever we need it. So let us prove our first theorem for this lecture. So the theorem I am going to prove is, let me call this I am, therefore I am. We are going to parameterize this with a proposition, and the theorem is just that P implies P holds. So far we have seen how to introduce and, or, and true, but here we have a different connective, so we have the implication. So the rule is that whenever you have an implication P implies Q, to prove it you have to write a function that takes as input a proof of P and produces a proof of Q. Since the proposition here is P implies P, I have to take a proof of P, and now I have to produce a proof of P. But I already have a proof of P here. It's called HP, and you can see that Lean has accepted my proof. Whenever we do not want to state the name of the theorem explicitly, we can use the keyword example. So to Lean, an example is like a theorem that does not have any name. So you should use example, the keyword example, uh, exactly when you don't need the theorem at other places. So usually this is examples are written just for exposition, and not to build up other theorems. So here I have written that for any two propositions P and Q, P implies Q implies P is true. So these arrows are just like function arrows. So when I write P implies Q implies P, Lean sees it like this. So P implies Q implies P. So we know that to prove this, we have to take a proof of P and then produce a function that can take a proof of Q and produce a proof of P. But I already have a proof of P, so I can write HP and Lean will accept this with a warning. So notice that it wants me that the variable HQ, which is a proof of Q, is unused, which is natural because here to prove this we actually don't need a proof of Q. So to silence this warning, you can say that the variable name is underscore, and this so Lean takes it to mean that you are not going to be referring to this variable. So you can also prove P implies Q implies Q. So here I have to take a proof of P and produce a function that takes a proof of Q and produce a proof of Q. Again, notice that HP is unused and Lean complains, so let me replace it with an underscore. So if you look carefully, you can see that the proof of theorem I am therefore I am appears here. So you can replace this part of the proof with the proof of I am therefore I am, and notice that I am therefore I am is parameterized by a proposition P, and here you want to apply I am therefore I am to the proposition we have named Q in this example. So I can say apply I am therefore I am Q, and we are done. I was able to do this because I am therefore I am was declared as a theorem, it had a name, and so I could refer to it. So let us see another logical axiom. So if you have propositions PQR, then I can say P implies Q implies Q implies R implies P implies R. So as before, we have to write a function because this is an implication. So first we have to take HPQ, which is a proof of P implies Q, and we have to write a function that can take a proof of Q implies R, as you can see here. And finally, I have to produce a function that shows this, which is a function that takes a proof of P, and I have to produce a proof of R. So if I put my cursor here, you can see that Lean is telling me HP has type P, and it is in the context of HPQ, which has type P implies Q, and HQR, which has type Q implies R. So since we have a proof of P and we have a proof of P implies Q, I can write HPQ HP, and notice Lean says that this proof has type Q, but it expected something to prove R. So we are using a new rule here. Recall that every proof of P implies Q is a function that maps proofs of P to proofs of Q. So HPQ, when given the proof of P, which we call HP, will produce a proof of Q. Now we need to map this proof of Q into a proof of R, But this is exactly what HQR does. So we apply HQR to this, and this proves this example. So notice that we have seen this function before. So this is just a function composition. So you take a function f, take a function g, and you take a data point x, and you apply f first, and then to the result you apply g. So let's say p and q are propositions. The rule called modus ponens in logic is usually stated as follows. So p and p implies q implies q. Notice that the statement we have to prove is again an implication. So we take the hypothesis as the argument. And if I move here, you can see that this has type p and p implies q. And now we have to produce a proof of q. So we need a new operation here because h is a proof of an and, but what we really need here is a proof of p and a proof of p implies q. We know that a proof of and must contain both these things. So we need some way to extract the proofs of the constituents from the and. So functions that does this are called eliminators or elimination rules. So if I type and dot left of h, so this whole expression is a proof of the proposition p, and I can do and dot right h, which is a proof of the proposition p implies q. And if you apply a proof of the proposition p implies q to a proof of p, what you get is a proof of q, which is exactly what we want. Let us try one more example. So let's say you have PQR, which are all propositions, and you want to prove P implies Q and P implies R implies P implies Q and R. So you should take a moment to see that this is true, and it's again an implication. So how do we prove this? We take the hypothesis. Now we have to prove the conclusion, but we see that the conclusion is again an implication. So we have to write a function that will take a proof of P, and now we have to produce a proof of Q and R. So the proof of Q and R can only be introduced by and.intro, and now I have to supply it a proof of Q. So let's look at the available data. So the available data is we have a proof of P and we have a proof of P implies Q and P implies R. So if we have a proof of P and a proof of P implies Q, then we will get a proof of Q. But luckily we already have this. So we can say and dot left h, which is a proof of P implies Q, and apply it to HP to get a proof of Q. Now we have to prove R. This is similar. So we can do and dot right h, which is a proof of P implies R, and apply it to HP to get the proof of R. We can make this a bit nicer. So instead of writing and dot left h, we can write h dot left as a shortcut, and instead of and dot right h, I can write h dot right as a shortcut. So what we have seen so far are so-called elimination rules for implication and. So an implication in the hypothesis you can eliminate by applying it, and an and proposition you can eliminate either through right or through left. There is an elimination rule for or. So if I check or dot elim, you can see that or dot elim is a proof of C. And what is C? So C is any proposition, but for the elimination to work, you have to give or dot elim a proof of A or B, a proof of A implies C, and a proof of B implies C. Notice that this rule is nothing but proof by cases. So if you have A or B in the hypothesis, then you can assume that the cases A and B are exhaustive, and if both those cases lead to C, then C must be true. So we will make use of or.elim to prove an example. So let PQRS be propositions. We want to say if P implies Q and R implies S and P or R, then we get Q or S. So we have to write a function and observe that H is a proof of the left hand side of the implication, and now we have to prove Q or S. So at the moment we don't know which one of Q or S is true, and a little thought would reveal that which of this is true is essentially determined by which of P or R is true. So this suggests that we have to eliminate the proof of P or R, which is obtained by doing H dot right dot right. So H dot right is shortcut for n dot right of n dot right of H. So H dot right is this highlighted proposition, and the right of that is this highlighted proposition. So we have to eliminate, and now we have to produce a proof of Q or S from a proof of P. If P is true, then we can take H dot left, apply it to HP to get a proof of Q. And therefore, we can prove Q or S by introducing the proof of Q via left. On the other hand, or the only other case is if R is true, in which case we can conclude that S is true by applying R implies S to the proof of R, and the proof is complete. So the proposition false cannot be introduced, but it can be eliminated. And if you look at the elimination rule, then you can say that false.elim produces a C where C is whatever you want, but you need a proof of false. So in logic, this is called principle of explosion. So if you have faults in the hypothesis, you can conclude anything. So stated in more familiar terms, if P is a proposition, then faults implies P. And you can notice that the proof of this is just faults.elif. Let us take a look at negations. So I want to prove for any proposition P, negation P and negation P holds. So for a proposition P, negation P is defined as P implies false. So we already have all the ingredients necessary to handle negation. It's just P implies false. So I have to write a function to prove it since it's an implication. And you can see that H has type P and negation P. And using this, we have to produce a proof of false. So the negation P here is a function that maps proof of P to false as stated. So if we take H dot right, it's a function that can take a proof of P and produce false. And we already have a proof of P, which is H dot left. So you can do H dot right, H dot left, and this would give you the proof of false, which in turn proves negation P and negation P. We can also prove one direction of the contrapositive equivalence. So if P implies Q, this implies that negation of Q implies negation of P. So we start by writing a function that takes a proof of P implies Q. So if I scroll over here, you can see that its type is P implies Q. Now I have to produce a function that takes a proof of negation of Q. Finally, I have to produce a proof of negation of P. But we know that such a proof must take a proof of P and produce false. So if you look at the current context, you can see that HPQ maps proofs of P to proofs of Q. HNQ can map Q to false, and HP has type P. So we can apply HPQ to HP. This will give us a proof of Q, and I can apply HNQ to this value to get false, which is what we needed. Observe that this proof is exactly the same as the proof of this particular example. So both these theorems have exactly the same proof. Finally, just to demonstrate the elimination of faults, let's say you have P and negation of P. With it, you can conclude whatever. So the idea here is to use elimination of faults. You take a proof of P and negation P, and you can apply H dot right to H dot left. And if I scroll here, you can see that Lean is complaining that I have proved false, but it was expecting a proof of Q. This is not an issue since you have already proved false. You can now prove whatever you want by applying false elimination. That's all for today. Thanks.